I got a call, so I had to stop recording for a bit. But let me just kind of go over the plan again. Um, Maybe I'll just record it again. Okay. So hello, my name is Jay or Jayhoon. Um, I'm recording this video because right now I can't YouTube stream. I was gonna do a live stream for this one, but I can't live stream until tomorrow. So this will just be a video, pre-recorded video of me explaining my plans going forward. Today's Saturday, February 28th of 2026. I'm going to be starting working soon, but I wanted to become a better developer. Uh, Before that, I have about a less than a month to finish all of this. Not all of this. I'm probably gonna get like one or one or two of these maybe in a month. That's my goal. Not too much. But the main picture is for me to become a better backend developer and learn more about distributed systems because that's what really interests me. But I've never really had the opportunity to learn it properly or learn it in a deep manner. My school I went to, they had distributed systems class. They were upper div class with really, really bad rated professors. So I decided not to take them and just study on my own. And here it is. Now that I have to study on my own, I realize that I need to do a lot of review of previous materials that I kind of glossed over or never learned. So right now, I kind of know the basics of everything, a little bit of everything. So computer systems and low-level architectures. I know what the CPU is, what it's supposed to do. These are, processors that fetches, decodes, and or executes. Wait, hold on. Is it fetch, decode, execute? Yeah, I think it's fetch, decode, executes instructions. Um, that's basically the definition, I think, but I don't exactly know the ALU or like the control unit. These are very foreign to me, so I'm gonna need to review these or just learn them, in my case. Cache hierarchy, I know these, but I'm just gonna review. Memory hierarchy. I also know these, but like I don't know them like well enough to teach it. So that's where my programming kind of declines. I want to be able to teach these concepts, IO fundamentals, and etc. So these are kind of just like ChatGPT generated, but in general, I do want a solid fundamentals of low-level architecture. Then we'll move on to operating systems. I don't know why it says practical. I don't know what that means. Like, I don't know why it says practical. I don't think that's very useful here. All right. Learn about the OS. What does it exactly do? It manipulates hardware to do things for us. I have a definition here. Let me remind myself. Also, I'm using Hennessy book to do this, and I've defined some of these already, and I'll go over these as well. System software that manages resources to provide common services, for example, these. Manage, handle, allocate, enforce. I'm not going to try to memorize that, but I think as long as I read more about the operation system, this will be another book. So ideally, I want to read the Operating System 3 Easy Steps. This is the book that was recommended to me a lot. Concurrency parallelism. I might like just do a little review on this. This is the part that I feel the most confident in because I've learned it recently. So might just not read a book on it. Just do like a review or like a quiz or like programming exercises might be enough. Networking is something I do need to really focus on. Never learned this ever. So I have an idea of what these are, of course, because I've done web development. but I don't exactly know how to teach this, which is my goal, right? I want to be able to teach this. And then data storage and databases. So this one, I already know what kind of textbook I want to read. I want to go for data intensive system, building data intensive systems. This is a book that has been recommended to me a lot, and I think this will be a good book for both of these, 5 and 7. And then these ones, I don't really care if I get to these, but yeah, those are a lot. So I think my goal is to finish until 6. If I can't do that, if I can able to go through 1 through 6, then I'm gonna be very proud of myself because that means I have discipline. That means I have, kind of the grit to go really deep into backend system, which is what I want to do um, before I turn, too old, like 25. So yeah, that's my goal. Before I turn 25, I want to be able to learn all of this. So I have around like a little bit, like 2 years for that. Um, yeah, so I'm gonna do that. And caching performance engineering, these are more, I think these are extra. So that's the plan. So today, what I'm gonna do, I think I'm gonna go review the definitions that I have, do a short little quiz. I have ChatGPT generating quizzes for me. I don't know if this is the best method. I've been doing kind of like the quizzes on the textbooks, which is like a little like there's like checkpoints here. Okay, I'm not sure. Hold on. Hennessy. This is free, by the way. Hennessy and Patterson computer architecture. This is literally free when you Google it, which is like kind of amazing. Oh, this is the 6th edition. Hold on, it might not be the right edition. But this book is really great. Even though it's a little outdated, I'm pretty sure the most recent version is like the 7th edition or something. I'm not sure. It's better load, man. It's better load. Or I'm gonna have to just download from Hennessy. Oh God. Alright, guys. I don't want to show you guys my Finder. I might leak something or something. Alright, Hennessy. Hennessy, Hennessy, Hennessy. Yes, here it is. Open with Chrome. So another thing about Chrome is this is this 6th edition? This is the 4th edition, right? The revised 4th edition. Yeah, that's what I thought. Okay, does this have quizzes? Does this have quiz topics? It has exercises, right? So hold on. We have 1.8. If Amdahl's law for measuring performance, I don't think I need to read these, by the way. Yeah, we have exercises. Oh my God, I probably should do this, huh? Okay. Um, I was here, by the way. Wait, where was I? Was I actually there? But yeah, okay, let me go through this with you guys so you guys are kind of in the same place as me. There's no need to, but I just want to review it. Um, CPU, brain of the computer, fetch, decode, execute, store result back to memory. First, straightforward. Additional functions are issue memory and IO requests, manage program flow and execution order. Registers are small temporary storage inside the CPU that temporarily holds data. The computer is an electronic device that manipulates information. Desktop computers, servers, embedded processors. Processors are basically the same thing as CPU. The processor responsible for getting data from the cache? Yes. All right, then we have the operating system. Don't know why I have two definitions. I can delete this. The operating system is a system software that manages hardware resources like the CPU, RAM, storage, network connections, I/O devices to provide common services such as managing the CPU execution through process creation, scheduling, and context switching, handles I/O operations via device drivers, buffering and interrupts, allocates and manages memory, enforces protection. I didn't really like this because we're going to learn about the operating system much deeper, and I wanted to lock in my full definition so I don't get confused later on if something about operating system is talked about, and I can just kind of always refer back to this definition and kind of remind myself what I wrote and relate back so this definition becomes stronger every time. I can't memorize this. I tried to, and it sticks around for a day and then it goes away because I don't fully understand the operating system. But the CPU, I kind of understand it, so that sticks. And the compilers translate code to assembly. Assembler take assembly, turns it into machine language. Okay, so I think I should probably add a diagram here. Code compile process diagram. It should have like linker. Yeah, like this. I like this. I like these kind of diagrams because it sticks. We have source file, preprocessor. it, it kind of runs all the preprocessor directives, all those kind of, include IOs, if def, those things. This is for C, by the way. Compiler translates code to assembly, right? It compiles the code to assembly. And then assembler takes the assembly into machine language. And then the linker turns it into an executable. Machine language is the same thing as an instruction, I think. Machine instruction. Yeah, I think it is. Definitely is. Let's add linker here. What does the linker do? Takes one or more object files generated by a compiler or assembler, combines them into a single executable file. Wait, object files? I'm confused. Hold on. To answer your question, yes, it's true. Assembler translates human-readable instruction into binary patterns that the CPU understands. An object file is more than just raw list of those binary instructions. Is machine code same as an object file? Think of the machine code as text and the object file as the book. Oh, so object file. So do object files include binary instructions? Like how text documents dot text is format any string that user has comparison. Alright, so object file is just this is .o file. Assembly is .i file. So I to S and O to X exe. Nice. Instruction assembly language is well, it's what we can understand as a machine language. Machine language is basically binary, but the assembly code is what we can perceive before machine can perceive it. Like it's the lowest level that we can see it before we can't see it, I think. Yeah. Now we have DRAM. We learn about DM. DIMM is just a module that contains the DRAM chips. SIMM have DRAM chips on the side. Data path, component of the CPU that performs arithmetic operations. Okay, I need to learn the different components of the CPU. Maybe it's already here. Okay, so do we have the data path here? Performs data path, the component, the CPU that performs arithmetic operations. So I need a CPU diagram that shows a data path. Is there no data path? Like, where is that? Okay, let me just ask ChatGPT real quick. This diagram, is data path included? Is the path the data is sent from and to, is that the data path? Is that why it's not mentioned here? Let me look at, where's data path? Like, CPU data path. Like, where is that? Where is the instruction memory, registers, and data memory? ALU is right here. So I guess, like, the path of that information, or is the path that instructions pass through, does that represent data path in this diagram? The data path explicitly inside this diagram isn't labeled. Okay. What the data path actually is. The data path is the collection of hardware components that store and operate on data. Typical data path components include registers. There's no registers. Can you find a diagram that encapsulates all these important concepts? I'm sure it can be able to find an image. What the fuck? Oh no. That's a bit complicated. That's a bit too much. Yeah, how does this even work? We have the program counter, which is a register. Okay. All right, maybe they'll also go over it in a bit. So I'm not really worried about that. Wait, where was I? Where was I? Where was I? Where's my notes? Okay. I don't know if this is true. I thought this was. This was the ALU. Yeah, I'm wrong, dude. This is not true. This is the ALU, man. Data path is something else. I don't really know why I said data path. Okay, here. The component that of the processor that performs arithmetic operation. Huh? Oh, data path contains the ALU. ALU registers, multiplexers, buses. Hold on. So ALU is the one that does the operating arithmetic operation. What does the I mean, it's in the name. Yeah. ALU does that. Registers are temporary like temporary storage inside the CPU that temporarily holds the data. So are there registers here? Like, why is that diagram missing so many things, man? That diagram is missing too many things. Data path is not there. Registers are not here. I don't even know where registers are then. um, CPU diagram registers. Okay, let me refer this back to our original. Yeah, we have registers here. I think I'm just gonna copy this thing. All right, nice. Okay, so let's move on. DRAM, we have DIMM, we have the ALU, data path. It's more fitting that this one's here. The control tells the data path memory I devices what to do according to the instructions. Cache memory, small fast memory, stored in the static RAM access memory. The ISA is the standard that describes how the CPU should behave. For example, like the x84, things like that, the architecture of it. And then the application binary interface encapsulates the ISA and the OS. We have the volatile memory, which is RAM. We have the non-volatile disks, physical hardware. Yeah. We have local and WAN. All right, transistor. Okay, so now we're on to 1.4. But before that, I was doing some quizzes. Let me close all these. I was doing some quizzes, and we've already done this. I don't know why this is still here. Yeah, this is the one I'm doing. This is the program counter. Which layer defines the set of instructions a CPU understands? I think it might be the layer defines a set of instructions the CPU understands. So it's gotta be like a little bit to the higher level, maybe? No, lower level. So like the CPU gets its data from the memory. And I think it might make sense that the operating system defines that because it can kind of like operate within that scope. I don't actually have an idea, I'm just guessing here. What actually executes instructions? The CPU, right? The compiler, the RAM, no. What actually executes the instruction? CPU. Alright. Program counter is right. This is incorrect. Okay, well, it's the ISA. Defines the set of instructions. Okay. One last question. Let's please move on. Oh my god. Alright, program runs the instruction. Add R1, R2, R3. Which layer defines that this instruction exists and what it means? I didn't learn this yet. I didn't learn this yet. Hey, I didn't. Hey, for day one, you are asking 1.1 to 1.3 strictly. Wait, I know actually. I don't wanna. Which defines this expression exists and what it means. So this is like assembly, right? I guess the ISA. I don't know. This is, yeah, I mean, sure. Day one mastery completed. All right, nice. Wait, is that our original plan? Hold on. 1.md, week 1 MMD. Day one chapter. We decided to do a lab, but I guess we're not gonna do that. Yeah, let's not do this. It's not really related to what we're doing. Performance and power wall. Micro benchmark a simple CPU bound loop in. Don't know how useful that is to me right now. I'm not gonna lie. The 1.4 doesn't seem very interesting to me. It's very important for sure. I've read it before I went to sleep once, but it's not very interesting to me. It's not very attractive because in our week, um, not this master plan, we don't really have performance, by the way. Yeah, I think I might have to redo the planning for the reading. Or maybe I'll just read myself. Because I skimmed 1.4. This is not really important because every single app that I'm going to build, the performance is going to be um completely different. But yeah, maybe I'll just skim through it again, which I did before, but I think this part is pretty important. Measuring performance times to measure performance. The computer that performs the same amount of work is the least time is the fastest. Yeah, I think the most important concept that I need to write down is the concept of throughput and performance. So here we have the CPU execution time and measuring single process. Different applications are sensitive to different aspects of the performance of a computer system. Many applications, especially those running on servers, depend as much on I/O performance, which in turn relies both on hardware and software. Total elapsed time, measured by a wall clock, is the measurement of interest. In some application environments, the user may care about throughput. Throughput is the amount of problems. Oh my God, what's like the, yeah, it's right here. Yeah, that's the only, I feel like that's the only important thing here. CPU execution time. All right, while that's happening, I'm gonna clip my nails. All right. What? I guess it is a very important concept. 1.1 to 1.6. What does that exactly cover? I need a, what's 1.1 to 1.67? Wait, 1.6? 1 to 1.6. Fine. You know what? I'll just read 1.4 for now. 1 to 1.6. This 6 sections. Okay, we're technically on day 2 then. Alright, I'm gonna read this again. It's throughput versus response time. Performance, primary concern with response time for the first few chapters to maximize performance. We want to minimize response time or execution time for some task. Thus, we can relate performance and execution time for computer X. This means that for two computers, if the performance of X is greater than the performance of Y, we have that execution of time Y is longer than that of X. If X is faster than Y, blah, blah, blah. And yes, relative performance. So performance, when you say performance, we're strictly considering execution time in this case. Yeah, we're not considering throughput yet, just the performance, the execution. Because performance and execution time are reciprocals increasing. What are reciprocals again? Like 1 over that, right? Increasing performance requires decreasing execution time. Increasing performance requires decreasing execution time. Increasing execution time. To avoid the potential confusion between the terms increasing and decreasing, we usually say improve performance or improve execution time when we mean increase performance and decrease execution time. Okay, that doesn't make any sense. Oh, depending on what we count, the most straightforward definition of time is called clock time, response time, elapsed time. Wait, can I fit it into CPU time spent in the program called user CPU time? Alright, I think I might continue tomorrow morning. This is a bit hard to understand. Yeah. Reread measuring performance. Didn't really understand. Alright, I think I'm gonna call it a day for today. Um, See you guys tomorrow, hopefully, or whenever I next upload a video. Bye bye.